Hello there, and greetings from Houston. My name is Neil Griffiths, and this is my graphical introduction to artificial lift. The title of the presentation is The Green Arrow, for reasons that will later become apparent. Now, I learned about artificial lift some 35 years ago, and I remember hours of tedium in the classroom as we pondered over equations like these. By the way, if you think these are bad, the outflow equations are even worse. We were introduced to a new nomenclature, or nomenclature as they call it over here, and I remember thinking at the time, there's got to be a better way of doing it. I didn't realize then that some 30 years later I'd be teaching artificial lift and would have to find that better way of doing it. So here we go. Let's start by drilling a well into the reservoir and considering an imaginary point at reservoir depths. This point will have a certain ambient pressure, known, unsurprisingly, as the reservoir pressure, or sometimes shut-in bottom hole pressure. The first concept I'd like to introduce is reservoir productivity, or more specifically productivity index, measured in barrels per day, the PSI. This is how it works. If we draw down, that is, lower the pressure at our imaginary point, then fluids will flow to that point at a specific rate. We then have a flowing bottom hole pressure at that point. If we draw down more, the flow rate will be higher. Simple. But the great thing about this is that all the relevant reservoir and fluid properties are built into this single line. The PVT properties of the fluids, the temperature, the porosity, permeability, height, net to gross, and the skin, which is the amount of damage the drillers do when they drill the well. So we have here a very simple but a very powerful tool. I guess I should admit to oversimplifying things just a bit, because when the ambient pressure is reduced to below the so-called bubble point pressure of the fluid, then liquids and gases separate and they have their own lines. A chap called Vogel had a lot to say about this back in the 60s, I think it was. But anyway, I think you get the message. So now let's complete the well and move on to outflow. Referring to the same imaginary point, a certain flowing bottom hole pressure is required to drive the fluids to surface. This is called the outflow performance of the well system. At low pressures and rates, the fluids tend to misbehave, but otherwise, what we see here is another very simple relationship. A certain flowing bottom hole pressure will drive fluids to surface at a certain rate. Higher flowing bottom hole pressure, higher rate. Simple. But the really cool thing here is that all relevant wellbore and fluid properties are built into this line. Again, the PVT properties of the fluid, the temperature profile, conduit properties, and tubing head pressure are all considered. Again, we have a very simple but a very powerful tool. So let's summarize. We have inflow and outflow relationships. Both refer to the same point in the well, and both are plotted on the same type of graph. That means we can cross-plot to see how much our total well system will produce. Brilliant! All things considered, our well will produce at this flow rate. Sadly, however, this is not always the case. Sometimes when we cross-plot, the lines don't cross, and so there's no unique solution and no flow. This is a dead well, and I think you all know where we're going now. This illustrates the fundamental need for artificial lift. But before we think about artificial lift, let's talk about other ways that we can make this well flow. Firstly, we can lift the inflow performance line. What we're doing here is increasing the bottom hole pressure without changing the gradient of the line, which is the productivity index. We make the lines cross and the well flows. This is typically what we do with reservoir pressure support, for example, water injection, produced water reinjection, or gas injection. Another thing we can do is reduce the gradient of the line. This is keeping the bottom hole pressure the same, but this time increasing the productivity index. This is typically what we do with reservoir stimulation, matrix acidizing, fracking, which of course is all the vogue, or various other chemical and heat treatments. Yet another way to achieve flow is to lower the outflow performance line. This is a little more complex. The shape of the line will actually change, but this is typically the effect of gas lift, which we'll come back to later, viscosity modifiers, and numerous physical so-called debottlenecking initiatives. So, with all that said and done, now at last we come to talk about artificial lift. Let's stop playing with the lines and think of some devious means to bridge the gap between them. This will also cause our well to flow. We don't have to do much to achieve a low flow rate, but we need to do a lot more for higher flow rates. Let's construct another line which tells us exactly how much artificial lift we need for a desired flow rate. This is called the well system curve, and wait for it, the green arrow. Fantastic! The green arrow tells us how much artificial lift we need, and rumour has it that an electric submersible pump, or ESP, may be able to help us. By the way, note it is an electric submersible pump and not an electrical submersible pump. Sadly, correct grammar is a scarce commodity in the oil field. But anyway, An ESP is a multi-stage centrifugal pump that generates pressure incrementally over its length. It consists of numerous spinning impellers that add kinetic energy to the fluid and an equal number of stationary diffusers that redirect the fluid upwards and into the next stage. This should not be confused with a positive displacement pump. Fluids can move through an ESP independently of the pump speed, and the amount of kinetic energy added to the fluid is a function of the relative speed of the pump and the fluid. Let me explain. If fluids are moving through the pump at a substantially slower speed than the impellers are spinning, then the fluid will be accelerated and pressure will be generated. This makes sense, but as the flow rate increases, this effect naturally becomes less. Conversely, when fluids move substantially faster than the impellers, the pump actually hinders the flow and acts as a choke. So now we're building an ESP performance curve, and since this curve will vary with pump speed, we'll expand the picture for variable speeds. At the far left of these curves, the pump will struggle against the near stationary fluid column, and the reactive forces known as downthrust will accelerate wear. This is bad news. Also, to the far right of these curves, the rapidly moving fluid will tend to lift the impellers, and this results in upthrust wear. This is also bad news, so we try to operate within these extremes. That completes our picture of an ESP operating envelope. Here is a real-life example. You'll see quite often the efficiency of a pump is also plotted. So now we have the amount of artificial lift our well needs as a function of flow rate, and the amount of artificial lift our pump can provide as a function of flow rate. I think you know what's coming next. We can cross-plot this to find the flow rate that our total system can deliver. And here we see the so-called operating point and again the green arrow. Right, now let's look at this from a totally different perspective. Here we see a plot of pressure versus depth, often referred to as a pressure depth traverse. Depicted here is a dead well with a deep static fluid level. The reservoir pressure, or shut-in bottom hole pressure, is insufficient to support a liquid column to surface, let alone produce at an economic rate. The static liquid level is naturally determined by the intersection of the fluid gradient up from the reservoir and the gas gradient down from surface. Now there are two things we must do to make this well flow, and these are not negotiable. Firstly, we must draw down the reservoir, i.e. reduce the bottom hole pressure. Then the reservoir will deliver fluid according to its productivity index. Remember we talked about inflow. Secondly, we must match the flow line pressure at surface, otherwise the fluids will not unload. Remember we talked about outflow. The problem is there's a big gap between the static liquid gradient and where we need to be. So let's run an ESP. It's sitting in the well at this depth, and now we'll see what happens when we switch it on. The pressure generated over its length enables us to achieve both of our objectives, drawdown and flow line pressure. And notice how the liquid level in the annulus drops as it responds to the new, lower flowing bottom hole pressure. And here's the green arrow. Now let's look at the ESP operating envelope, and here again is the green arrow. But with variable speed, we have a level of flexibility. We can speed up the pump and increase the drawdown and flow rate. Conversely, we can slow down the pump and reduce the drawdown and flow rate. Before we move on, I should admit again that I've been oversimplifying things just a bit. In reality, with friction, compressibility and gas breakout, the gradients we see are actually curved like this, but I think you get the message. Now let's move on to gas lift. We start off the same. We must somehow draw down the reservoir and match the flow line pressure, but now we adopt a different approach. We install a valve in the completion string which allows us to inject gas from the annulus into the tubing. The valve sits at this depth. Now watch what happens when we force gas into the annulus. The gas displaces the liquid in the annulus down until it reaches the injection point, and then, when it bubbles into the tubing, it lightens the fluid column progressively from the bottom up, and see what happens. Again we've achieved both of our objectives. We have drawdown and flow line pressure. Notice, however, that the drawdown is less than that achieved with an ESP, and there comes a point when increasing gas injection rate has diminishing return. There is naturally a limit to how much you can do by manipulating fluid gradients. I should also mention that in a real well, there are often several unloading valves to reduce the gas pressure needed to displace the annulus, but I think the message is clear enough. And so to summarize, ESPs have more flexibility and can typically achieve higher drawdowns and flow rates than gas lift, but they introduce a higher degree of downhole complexity and risk. The understanding and management of ESPs is therefore much more onerous, and mistakes can be very costly. Gas lift, though unable to achieve the same flow rates, is more forgiving and cheaper and simpler to operate. I guess that invites a discussion on artificial lift lifecycle management and the rigless ESP deployment technology provided by Zytex, but that's for another day. Anyway, I hope you enjoyed this introduction to artificial lift and trust you now all understand why it's all about a simple green arrow. Bye for now.